All right, so in the last part, I showed you guys how to do tasks using the Hugging Face pipeline API. So a pipeline is just the highest level way of doing something. It's very easy, but now we're going to get behind the scenes a little bit so you can actually understand what's happening, how you can actually use these models to do stuff, right? So for example, here we bring in the pipeline from Transformers. We're doing a text classification pipeline, and we're going to classify the piece of text that says, I love this library. And so by default, it's going to use a fine-tuned model called Distilbert Base Uncased Fine-Tune SST to English. This is just a model that's configured with that pipeline by default. And so when I run it, I get a positive sentiment with a score of 99.9%. So it's very confident that this piece of text here is a positive sentiment, which it obviously is. So this is very useful if you want to do stuff really quickly, you just want to get something done. There's already a pre-made model to do it, and it hooks directly into the pipeline. If you want to fine tune your own model one day, or maybe you just want to use another model that's already fine tuned but isn't really compatible with a pipeline, it's important that you understand what's actually happening behind the scenes. So let's try using the same exact model that was used by default in the pipeline, but manually, so we can see how it actually works. So pretty much anytime you're going to be using a language model within Hugging Face, you're going to need two things. You're going to first need a tokenizer, which is generally responsible for breaking up the text into tokens. We'll talk more about that later. And then you need the actual model itself. So that's why we're going to bring in auto tokenizer and auto model for sequence classification. So we're going to create a new tokenizer by doing tokenizer is equal to auto tokenizer dot from pre-trained, because we're trying to bring in a pre-trained model. And now we just want the name. So we're just going to copy the name from up here, just the ID of the model, and paste it. So now, if I was to run this, what it's going to do is download this model. It's already downloaded because we used it in the pipeline, but if you've never used the model, it's going to download it, so it may take a second for the first time. After you have the tokenizer, you need the model itself. So the model is equal to auto model for sequence classification from pre-trained, and then again, you pass in the same ID of the model. So you may notice that even though we need two different components, the tokenizer and the model itself, they both correspond to the same model name. This is because when language models are trained, they're trained using a specific tokenizer. So anytime you want to use a language model, you have to use the tokenizer that it was trained with. They are tied together. So we'll be doing a deep dive on the tokenizer, of course, but for now, just know that the tokenizer is responsible for splitting the text into tokens, which can be like words or subwords, or even characters, and then converting them to things called input IDs so that the model can understand it. Because the model here that we have that we're bringing in doesn't just take in a piece of text like this. That's what the pipeline abstracts for you. You have to take the text, break it up into tokens, and then convert those tokens to actual numbers or input IDs that the model can then interpret and convert to embeddings and stuff like that. So you can really just think of the tokenizer as the thing that pre-processes the text so that it can be fed into the model, okay? As for the model itself, it's a pre-trained Distilbert model that was fine-tuned for a specific task, which is sentiment analysis. That's why it's able to output a label of positive or negative, essentially, okay? By a pre-trained Distilbert model, I'm saying that this was a language model called Distilbert, and it was pre-trained on a large amount of text, and that's it. Distilbert itself was not trained for the purpose of sentiment analysis, right? So what happened was the base pre-trained Distilbert base uncased model was then taken and then fine-tuned specifically on a specific data set for a specific task, which is, again, sentiment analysis. That's the part that we're going to be learning how to do next episode. We're going to learn how to take a base pre-trained model, such as BERT or Distilbert, and fine-tuning it for a specific use case. I hope that makes a little bit of sense. It's perfectly okay if that doesn't make a whole lot of sense because, again, we're going to be deep diving into it in the future, all right? This is just so you can get going. Let me show you another example here, okay? So we can actually just output the model itself, the variable, and that will print it to the console. This may look familiar to you if you're familiar with PyTorch. This is the architecture of the model itself, all the layers and everything like that. You don't actually have to understand what all these little things do, like the transformer blocks and all that stuff. That's pretty advanced. But if you look closely here, we can see that it's pretty much split into two different sections. First, we have Distilbert, which again is the actual pre-trained base model that we're using. So that's the first section here, this whole thing right here. And then on top of that is called the head. We've built as basically a submodel layer on top of that Distilbert base model layer that does the sentiment analysis classification. So we're taking basically the raw output of the Distilbert part of the model, and then we're passing it directly into a linear neural network layer, and then we're passing it then into another layer that outputs two features. And the two features, as you can imagine, corresponds to the sentiment analysis output that we want, which is positive or negative. All right, and then we have some dropout on top of that. So if you've ever built a binary classifier or a multi-class classifier, for example, just a standard neural network, not anything with language models, this part should be familiar. It's just simple neural network layers, and then the final output is the amount of labels in your problem that you're trying to predict from. So if it's a binary classifier, you're going to only have two, of course. So that is why we specifically do here auto model for sequence classification. When we do for sequence classification or for summarization or whatever the problem is, that is adding on to the architecture of the head here. So the head will be whatever head matches whatever problem you're trying to do. Okay, so if I was to remove this, if I only do auto model, which is possible, you can use auto model. If I do auto model from pre-train, it's only going to bring in that base model part of it. So let's try that. There we go. So we can see that when I print it out, we only get the Dilbert part of the model itself. There's no head on top of it. So this will not be able to do any sort of sentiment analysis for you. So back to what we're trying to do. For anything that requires language in Hugging Face, first you want your tokenizer. So we're using auto tokenizer and bringing in the specific tokenizer for the specific model that we want. And then we're also bringing in the model itself for sequence classification with the same model name. All right. So now let's talk about how we can actually use the model and classify some text. So let's just say we have some text like, I love drinking Red Bull and watching the news. Something very simple. And so we're going to try classifying the sentiment of that. I'm sure you could guess we need to first use our tokenizer because, again, the tokenizer basically prepares the text for a format that the model understands. So we're going to do inputs is equal to tokenizer, and then we're going to pass in simply the text. And then we're also going to pass in the return tensors and then put PT, okay? So what this is doing here is we're telling it that we're using the tokenizer, we're passing the text, so it's going to tokenize that text, and then we're telling it to return it in the format of PyTorch tensors. That's what that means, PT PyTorch. So if you want to, you could do, for example, TF for TensorFlow if you're using TensorFlow. All right, as you can see, we got two things in this object here. We got input IDs as a tensor because we told it to return as a PyTorch tensor, and then we also got a attention mask as a tensor as well. The input IDs is the most important thing. These are the tokens converted to their unique IDs within a dictionary or a vocabulary. So again, yet again, this is something that we'll dive deeper into so you'll fully understand it in a future video. But basically what's happening here is we're taking the text, converting it to subtokens. So at a high level, it could be just every single word is a specific token. So I love drinking, those are all different tokens. And each of those tokens are mapped to a dictionary or vocabulary that we've created for our tokenizer and our model. So every token will be converted to a number because a model only understands numbers. That's the input for the model. So if we want to visualize it, we can actually convert our input IDs back into the tokens, which is really helpful to actually visualize it. So we'll do tokens is equal to tokenizer dot convert IDs to tokens. And then we specifically want to get the input IDs, so inputs. And so that will give us this tensor here. And then we only want the first row of that tensor basically because we only have one piece of text that we've converted. And then we're going to do tokens. So let's take a look at what that looks like. So here we go. This gives us insight into how the tokenizer actually took this piece of text here and tokenized it. So we can see that it first added these special tokens here. Different tokenizer and different models are going to have their own special tokens. But besides that, we can see that all the text of our original piece of text was converted first to lowercase because we're using a lowercase Dilbert model. So it's all going to be converted to lowercase. But you can see here for the most part that all the text that we provided to the tokenizer, it was basically split up into individual words except for Red Bull, because in the vocabulary of the tokenizer and the model, you can't really expect Red Bull to be a specific token that I would recognize. It's a very rare word compared to these other words here. So it was split up into subword tokens of red and then BU and LL. The hashtag corresponds to it being part of a previous word, essentially. So they're connected. So basically, our tokenizer took our text, normalized it into lowercase, added special tokens, split up our text into tokens that it recognizes, and then converted those tokens to their unique IDs. The input IDs is what they're called. The attention mask is something that we'll learn about in the future. It's just a way of knowing, telling the model which tokens are important to pay attention to when you do something like padding, for example, okay? So now the fun part, we can actually use the model. So we're going to do import torch, because by default, transformers, the Hugging Face transformers library is going to use PyTorch models, right? And we also told it to return it to us as PyTorch tensors. And then we're going to do with torch.noGrad, because we're just using the model for inference. We're not actually doing anything like updating the weights of the model. So we're going to do outputs is equal to model, and then we're going to pass the inputs like this. So we're using a model that we imported before using the auto model class. It's a PyTorch model behind the scenes. And we're passing in the inputs, which is the output of the tokenizer, into the model to get some output. So let's try it out. That was fast. So you can see I gave us a sequence classifier output. The important part here is this part here, the output of the model, which is logits, which is a tensor of two numbers. So in a classifier neural network, you're going to have the logits, which are just the raw numbers of the final output layer. So we could do, for example, logits is equal to outputs dot logits. And we'll just print those out. So it's just the raw numbers from the last layer of the neural network. So now what you do in a classification problem is you convert the logits into probabilities. So we'll do probs is equal to logits dot softmax on the first dimension. So we are applying a softmax activation to that last output to convert the raw logits to probabilities, because in a classification problem, the probabilities indicate which label that is being predicted. So the index with the highest probability corresponds to the label that is being predicted. In this case, it's obviously the second one. So whatever corresponds to the second index would be the second label, and that's the prediction. So this piece of code here will take that probability tensor and then get the highest index. So we get the predicted class, which is index number 1. So we basically want to figure out which label corresponds to index number 1. And so built into the model, if we do model.config.id to label, this is a mapping that converts the specific ID to a label that we can use. So if we just do this, for example, we can see that the mapping has 0 for negative and then 1 is positive. So if the predicted class index is 1, then obviously it's a positive sentiment. So we can run this now, and we can see that the predicted label is positive and then has a score of 99%. And that is it. That's how you can use a fine-tuned model to get a prediction. So as you can see, it's much more involved. You have to remember how to do all of this and use a PyTorch model. If you've used PyTorch, it's not really that hard because it's still a limited amount of code. You don't have to actually train anything at this point because it's already trained for us. But this is the thing that the pipeline API is abstracting for you. If you use a pipeline, you simply get the output directly. It's very, very simple. If you use the Hugging Face transformers tokenizer and model directly, it's a little more involved. So hopefully this demystifies a little bit what happens behind the scenes of a pipeline. This is only one example of many of how we can use Hugging Face transformer models. The general gist of it is that we need to bring in a tokenizer for the model as well as the model itself. The tokenizer is tied to the model, so it needs to be the same model ID when you bring it in. And then when you're trying to use the model, you first take the text, pass it through the tokenizer to get it all tokenized and everything like that for the model to understand. And then you pass in those inputs from the tokenizer to the model itself to get the output. And then you parse the output to get it in a format that you want. In this case, I just printed out the predicted label. Now I have a challenge for you. I'm not going to do it because this video is already pretty long. I'm going to do this in a future episode. For now, try this on your own. I want you to try taking this model on Hugging Face. It's a tone model. So if we go to Hugging Face here, we can simply put the model ID in there, go to it. It says, Finbert is a BERT model pre-trained on financial communications text. The purpose is to enhance financial NLP research and practice. So the idea behind this model here is it simply takes a piece of text and classifies it into a tone, so neutral, positive, or negative. Overall, it should be the same exact approach. You want to bring in that tokenizer, bring in that model, run the model based on the tokenizer output, and then parse the results to get the actual label. So give it a try yourself, see if you can actually do it, and then in a future episode, I'll show you guys how to do it, okay?